parts. One is the magnitude. And the magnitude, yeah. For this case, the magnitude is 1 over the square root of 1 plus omega squared. So it's going to be something like this. Okay, the first one is the magnitude of the transfer function, the magnitude. And then the second one is the place. Okay, in this case, that's the arctangent of omega. Arctangent of omega. Now, these two figures are very important for classical control, for classical control. We will see that sometime later. And we have an important terminology, which is bandwidth. Okay, or by the way, dB. This plot, the magnitude of the transfer function is in terms of dB. The unit is dB. Okay, what is the dB? For the dB divided by two definitions here. First one, if we are considering the power, then dB is equal to 10 times the log. This log is 10 base, okay, base 10. Base 10 log. So the dB is divided by 10 base 10 log, W over W reference, or output over input. But if we consider, say, voltage, in this example is voltage, then that is dB is given by 10 times log base 10, okay, voltage output over voltage input, quantity squared. That is the definition for dB. Now, another terminology which is very important, that is the bandwidth. Okay, the bandwidth is when the output magnitude becomes negative 3 dB, okay, at a certain frequency here. Then this frequency up to 0 is called the bandwidth of the system. It's called the bandwidth of the system. Okay, negative 3 dB. That is about 1 over the square root of 2. So when your magnitude drops to 1 over the square root of 2, okay, forget about dB. Okay, let's use the magnitude directly. Suppose we don't use the dB. If we use the magnitude directly, initially it's 1, okay, and then up to a certain point, this becomes 1 over the square root of 2. Okay, then we call this frequency the omega cutoff. Okay, omega C, then this frequency is called the bandwidth of the system. When the magnitude drops to 1 over square root of 2 compared to the 0 frequency, then this frequency is called the bandwidth of the system. Bandwidth of the system. Now it's a very important terminology. Okay. So it's given by, see, I've given you this one, 10 times log 10. Okay, log 10 base, okay? And then 1 over the square root of 2. Quantity squared. You can find this is roughly equal to negative 3 dB. Okay. All right. So that's the body plot. Okay. Okay, so let's move to another important topic, complex exponential Fourier series. It's complex. Okay, suppose we have a periodic function x of t. In general, this can be a complex function, but it is a periodic function. And then let's assume the fundamental period of this function is t sub 0. Okay? Then the complex Fourier series is given by, of this function is given by x of t is equal to a coefficient x of k times e to the j k omega sub 0 times t. Now this omega sub 0 is given by, or defined by 2 pi over t sub 0. Okay? And then we have a term for this. This k omega sub 0 is called discrete frequency. K is from negative infinity to positive infinity. Okay? Alright, before we try to determine the coefficient x of k, we have to find the norm of the function e to the j k omega sub 0. Okay, so j Now, even though those complex functions, equal j k omega sub 0 times b, these are functions. They are function of time. They are function of time. Okay? In general, this function t can be negative infinity and up to positive infinity. Let's assume you can imagine, make your life easier. These are kind of vectors. Even though they are functions, but they are kind of vectors. So we have a set of vectors, okay, but they are orthogonal. Orthogonal functions. There are many numbers of the functions. Okay, maybe we give you another one. Yeah. All right, but then we are going to prove that they are orthogonal. They are orthogonal. Kind of, remember in your high school you have left vectors. If I have two vectors which are orthogonal, okay, suppose I have two vectors, vector A and the vector B. If vector A and the vector B are orthogonal, we have inner product A plus B equals 0. If A is orthogonal to B, right? Am I right? Okay, you know that. Okay? Okay, so we have to prove that first, and then find the norm of the functions. So, similar to the inner product for a function, we use integration. And kind of, this is, we use that on the inner product. K, omega 0, P, K, omega 0 times P. Okay, the inner product of these two functions, similar to the finite dimensional vector. We are considering infinite dimensions vector, so it's a function. Sorry, I have to use complex functions. Sorry. So that will be minus. This will be minus. Let's treat that like a regular function. So I have to here from periodic function, so I need to integrate from, sorry, I need to change the other row. Sorry about this. Maybe just simply 0 to T0. It's a periodic function, so okay, two cases. If A equals F, then this becomes e equals 0, but it's 1. If this becomes this one 0. Now, if A is not equal to F, and this is equal to A minus F. This is first one becomes T0. Okay, what about the second one? A minus L, E0 minus 1. But omega 0 is 2 pi. And this is omega 0. Right? Omega 0 sine of this. Omega 0. Alright, now since omega 0 is 2 pi over T0, so this is 2 pi over T0 times T0, that's 2 pi. So this is 1. Okay, so eventually it's 1. So that's 1 minus 1, that's 0. So you can see that if K is not equal to that, then the inner product of these two functions is 0, which means they are orthogonal. They are orthogonal. Okay? That's good. That's what we need. Okay, then how do we determine the x of K? Okay, so now let's write the x of t in terms of those basic functions. Okay, now again, remember that how do we find a coefficient when we want to determine the component of a vector in a three-dimensional space? Okay, and here we have a vector. Suppose this vector is given by, let me put a vector, okay, vector x. Just call this vector x. Okay. Let me open the slide. So this vector x can be written as x1 times I plus x2 times j, and then plus x3 times k. And maybe you may use E1, E2, E3 instead. E1, E2, E3, so on. Okay, and those E1, E2, E3, they are orthogonal to each other. So E1 orthogonal to E2, E1 orthogonal to E3, and also E2 is orthogonal to E3 as well. Okay? Now, let me ask you, how do I determine x1? How do I determine x1, the coefficient, or the projection? How do I determine the projection? I know E1, E2, E3 are orthogonal. And then in this case, how do I determine the projection or the component in the E1 direction? We take inner product, right? X dot E1, right? Then I have x1, E1 dot E1, and then x2, E2 dot E1, and then x3, E3 dot E1. Now, since I have assumed in the beginning E1, E2, E3, they are orthogonal to each other, so it's a basis, orthogonal basis. So E2 dot E1 is 0, E3 dot E1 is 0. So my component x1 now is simply x dot E1, and then divided by E1 dot E1, right? And similarly, I followed a similar procedure. I can find x2 is equal to x dot E2, and then over E2 dot E2. And also for the x3. E3 dot E3. So this is the concept we are going to apply to this case. Even though they are functions, but we can use the same concept. We can apply the same concept to the function. Okay? So now if I want to determine, say, if sub k, one of the coefficient, then what I can do is to take inner product with E sub k omega 0 t complex conjugate. I take the inner product because this is a complex function. So I have to use complex conjugate. Okay? Be careful here. Okay, smear. Here I use complex conjugate. Okay? So that means I'm going to multiply every term by the complex conjugate of e to the jk omega sub 0 times t, and then integrate the function, integrate the product. So that will give us only one term left. We use a space here. And we bring that here. Sorry, need a space. Okay, so this
For simplicity, we
we're from 0 to t sub 0 in one period. E to the k omega sub 0.
stop.
Yeah. So here I replace the function x of t by the Fourier series of the function. And it allow me to call that Fourier series at this moment. And as we have proved in the previous page, only one term will be non-zero. Okay? Only when k equals f, that is not any function. So this is equal to x of k plus omega. And that is t0. We have done this one. Oops, sorry. X of k times t0. That means the coefficient, okay, kind of this projection, coefficient is equal to 1 over t0 times the integral. Okay? And again, x of t is given by okay, just repeat that here. Okay, this is the fundamental concept of a Fourier series extension. Okay, one more time, let me remind you, in order to have a Fourier series, the function we are considering must be periodic. Okay? And for non-periodic function, we have another one to deal with that. That is the Fourier transform, but it's not in this chapter, it is in the next chapter. Okay? All right, any question for the derivation here? Any question?
All right, if there's no question, if you have no
Question, then let's move on to the next. Okay, what about if we consider a real function? Okay, that is function. Okay, maybe we want to. Whether this is a good equation. Okay, real value function. Suppose that is the case. Okay, for this case, what can we say about the coefficient? Then we make a k star. Okay, we take the complex conjugate from the coefficient. So that will be 1 over T0. The complex conjugate over the entire product of the function. But since the x of t is a real function, so this is equal to x of t again. But then the exponential function now switch to k omega sub 0 times t. And then I'm going to make a small trick here. Okay, so now I replace the k, the index k by negative k. So the minus sign now is equal to j, and this turns out to be the coefficient of x of negative k. Okay, that's a very fundamental, but it's very useful. It's very useful. Okay, any question up to this moment? Okay, so now let's go back to the Fourier series expansion of the function again. So f of t is
Summary.
x of k, the coefficient x of k times the complex function e to the j k omega sub 0 times t. Okay, then this also can be replaced by cosine k omega sub 0 times t plus
K sine K omega sub 0 times T.
Alright, so now I'm going to split the two terms. now, if we are considering a real function, then the complex Fourier series expansion also can be degenerated to Fourier cosine and Fourier sine series expansion. Okay, recall that in the previous step we have proved the complex conjugate of x of k is equal to x of negative k. So here, the x of negative k can be replaced by x of k complex conjugate. Okay, so x of k suppose is equal to ak plus j times dk. Okay, now maybe c is d. Okay, suppose that you c is a d, and then try dk plus j times dk, for example. Then x of negative k will be the complex conjugate of this guy. It will be ck minus j times dk, right? Okay? And then we make it go here. Okay, so we let x of k be ck plus j times dk. Then there's a negative k will be the complex conjugate. Okay, as we have proved here. So the x sub e k, the even part, will be 1/2 xk plus x negative k should not be equals to ck, the real part of the coefficient of x of k, and the whole part will be 1/2 j x of k minus so these two ck cancel out. So we have 2 times j dk times j, so it equals to negative dk. Okay? So this can be further simplified to, this can be replaced by the real part of x of k. Okay? So this can be replaced by ck, and then x of ok, the whole part. This guy can be replaced by negative dk. Okay? Any questions? All right, let's take a 10-minute break.